Hello. In this video, I'd like to talk through most of the problems that come from our Math Excel assignment, the Test 3 practice. I did mark this as optional, but I do think it's worth your while to practice with these. It'll give you a better understanding of the behavior of some of these exponential functions, and it'll also perhaps give you another way to think about these exponential equations or logarithms that go with them. So in problem number 1, we're told that the rate of inflation averages R per annum or per year over n number of years. So the amount A, the amount of money A that P dollars will purchase, so in other words, purchasing power here, the dollar in today's market is not going to be the same as a dollar in future markets, is based upon this particular function. And we would call this an exponential function because the variable n is our independent variable. That variable is stashed here in the exponent. The values for a, p, r, these can all be established in a particular scenario. We would call these parameters. And once we settle on 2 of the 3 parameters, then we can utilize the function based on n. So in this case, we really only have one parameter value given to us. We're told that the average inflation rate is 1.7%. So that's our R. That's our rate per annum or per year. But what's interesting is that we want to know how long it takes until the purchasing power is cut in half. Well, that's a clue in and of itself. We're saying that the amount that the purchasing power is worth, this A value, is half of what P value is to start with. And P is just, well, we can just call it some letter P. It doesn't matter what number you use here. If we assumed or made a guess that P was worth $50, then in a certain amount of time, half of that would be 25. And we could use 50 or 25 in place over here. But regardless, after the very first step when solving this problem, and I'm just going to erase these numbers for clarity here, regardless of what number we choose, whether I write a number here and then half of that number on this side of the equation, the very first step is to divide both sides by this value. In this case, it's P. If I had 25 divided by P, I'd be left with a half. If I had 50 divided by 100, I'd be left with a half. It doesn't matter whatsoever how much money we start with. So even though there was no P value given to us, we can still set up and solve this problem. Now the R value, I don't think they did a really good job. Oh, no, I take that back. They did. They did explain that R is expressed as a decimal. So even though R is 1.7%, we need to think of that as a decimal, 0.017. So if you recall, 1.7%. If you recall how to convert a percentage to a decimal, we simply divide this by 100, 1.7 divided by 100. Or the alternative, if you can keep it straight in your mind, is to move the decimal 2 places to the left. And we now have 0.017. So anyway, if we simplify this exponential equation, we have 1/2 equals some base value, whatever 1 minus 0.017 is. I'm not going to do that math just yet. Raised to the power of n. And we can rewrite this as a logarithm in order to isolate our value, n. And as it turns out, a logarithm with the same base as our exponential, evaluated at 1/2 instead of being evaluated at the exponent of n. But the logarithm evaluated at 1/2 would give us our n value. And if I go to the calculator, I would get 40.4258 as a return. So what we're saying is that if the rate of inflation of buying power, if you will, increases at a rate of 1.7 per year in approximately 40.4 years, the money that you have today would have half of the purchasing power at that time. For number 2, we're told something about this zero coupon bond. Now, much like number 1, in number 2, you don't have to be an economics expert to be able to address and account for the math in this particular problem. But evidently this zero coupon bond is a bond that is sold now at a discount and will pay its face value at the time when it matures. No interest payments are made. So that's like saying I'm going to buy this bond that will be worth $1 in the future, but I'm going to pay maybe 92 cents for it right now. So if I pay 92 cents out of pocket, then when it matures, if you will, it will pay me back $1. So I would earn 8 cents on each one of those bonds that I purchase. The only piece of outside information that would be required here is to recognize what is the format of the exponential growth formula for currency when we compound at a discrete period of time versus compounding continuously. These two formulas would be provided on the upcoming test. They're also available if you click the question help button if you were to view an example on Math Excel. They'll give you both of those. So if we were to compound 12% quarterly, and we would be using this particular function for discrete compounds, that means individual compounds, not a continuous compound, then what we're saying is that in 20 years' time, so 20 is going to be our t value, the amount that the bond is going to be worth is $10,000, so the ending amount is $10,000. We don't know how much we'll pay for it right now, the present value p, so that's the unknown. And if we have a bond that's going to pay 12% interest, that would be our R value, but keep in mind that the interest rates are reported as a decimal. And we're compounding our interest quarterly, and would be equal to 4. So interest rate, the number of times that we compound our interest per year, n is 4. We have a t and an a value. So when I substitute numbers into the supplied equation, the one here, our objective is to solve for p, the present value today. Now what's interesting is that this p-value is multiplying by this expression that I just put in the orange brackets here. And so if I were to isolate p, if I were trying to solve for p without reaching for the calculator, then I would literally need this $10,000 number divided by everything that's written inside of this grouping symbol. And that's exactly what I have set up in my calculator. I have $10,000, which was on the left side of the equation, being divided by the remaining expression, and this would isolate p. This is r1 plus r over n to the power of n times t. When I press enter here, I see the result, 939.77. We're only rounding to 2 decimal places here because this is a American currency question where we're talking about dollars and cents. So those 2 decimal places should suffice. But what I find particularly interesting is that this is an exponential equation, a problem that involves an exponential equation, yet we didn't require any logarithms to solve. And that's perfectly fine. We encounter that from time to time. In a similar question, we're given much the same information. We have the same t value and a value. We're solving for p, but now we want to know what if our interest was compounded continuously. So an infinite number of compounds, infinitely as often. Well, that would require a slightly different equation, but the end result isn't all that different. If we were to purchase these bonds and their interest rate was compounded quarterly, or calculated just 4 times per year, then we would be required to pay $939 for that bond. However, if our interest was compounded an infinite number of times per year, the amount of purchase isn't that much different. We would only have to pay $907 for that investment to be worth $10,000 in the future. And I would set that up much the same way in the calculator as I did before. Our ending amount A, $10,000, is being divided by e to the RT power. This would isolate the value p in our algebra, and we'd end up with $907.18. Now here again, in most problems, I would prefer to see 4 decimal places as your result rounding to 4 decimal places, but the instructions here on Math Excel said to round to the nearest cent, or 2 decimal places. So in this next example, again, this is not a formula that we're familiar with. We haven't practiced much with it, but I think by reading for context clues, you should be able to work with it. This formula can be used to find the number of years required to multiply an investment m number of times when r is your interest rate compounded a certain number of times per year. In economics class, we often hear of the rule of 72, and I'll let you research that on your own, but that's a roundabout way or an approximate way to calculate how much time it's going to take for your money to double or triple, let's say. But this particular formula is a bit more precise, and provided that your institution that you're investing with can guarantee the number of compounds per year as well as the interest rate, then this will be a more precise solution as well. So part A, how many years will it take to double the value of an IRA, an individual retirement arrangement, that compounds quarterly at a rate of 13%. Now, to double your investment, that would imply that your M value is equal to 2. Your R value of 13% would be reported as 0.13, because we always report these percentages as a decimal. And then finally, to compound our interest 4 times, or quarterly means to compound it 4 times per year, and we have an N value of 4. So we have all components of this equation except for t, so I'm just going to build the fraction as it's listed on the right side of that expression. We need, in the numerator of a fraction, and don't forget I pressed Control Divide to create the fraction, but in the numerator I need a natural logarithm, ln, not in, but ln, of m, and m stands for 2 here because we're doubling the value of the IRA. We'll drop down to the denominator, and I need an n value. N is equal to 4 because our interest is calculated or compounded 4 times per year. We multiply by the natural log of 1 plus the rate divided by n. So the rate in this case is 0.13 for 13%. And again, we are compounding our interest 4 times per year. So each time we compound the interest, it's worth 13% divided by 4. So I think this expression matches what was given to us in Math Excel. And when I press enter here, we get a result of 5.4181. And I would call that 5.4181 normally, but in this case, since the instructions did say to round to do 2 decimal places, we'll call that 5.42. Now, let me remind you again that if your calculator isn't displaying all of these digits, we can easily fix that, especially for those of you that just recently installed this on your computer. If you press the on button until you get to this home screen, you can choose option 5 for settings, and then option 2 for current settings. You want to make sure that your display digits are set to float and not float 6 by default. Float 6 is sort of like asking the calculator to return 6 significant digits, and sometimes that's enough decimal places and sometimes it's not. If we change to float, then the calculator will display as many decimals as possible at all times. So we see a bunch of them there, and we can round as needed. 5.418 does round up to 5.42. So evidently it takes about 5.4 years in order for the individual retirement arrangement to double. So the next logical question would be, how long does it take for the IRA to triple? Now, it would have been nice if the interest rate was the same at 13%. That way we can compare apples to apples, but we've got to go apples to oranges here because there's a slight change. We are tripling our money, so M is now equal to 3. We're also compounding our interest monthly this time, not quarterly, so N is equal to 12, and then finally our value of 0.07. So in this calculator, I could rewrite that whole thing, but what might be easier is if I just press the up arrow until the last expression that I want to copy is highlighted. Once it's highlighted, I just press enter and it copies down. And now I can make the changes as needed. Instead of doubling our money, we're tripling it, so I'll change this to 3. Instead of compounding 4 times per year, we're compounding 12 times per year. I do need to change that in both locations. And then lastly, our interest rate is not 13%, but it's 7%. Oops, don't need that extra decimal here. So I think this expression ought to do it. When I press Control Enter, I see that 15.7402 years would represent the amount of time necessary for this investment to triple, given those new parameters. We are only interested in 2 decimal places, according to the instructions, that is. And since we're only interested in 2 decimal places, then 15.74 would be a fine answer. For question number 4, this is similar to the problems that we saw a little bit earlier when we were talking about the average rate of inflation. But with number 4, we don't know the rate of inflation, and we're actually using the Consumer Price Index to determine that. And so we're told that the CPI, or Consumer Price Index, does indicate the relative change in price over time for a fixed basket of goods and services, or a collection of goods and services. So this formula here, the Consumer Price Index for today, is equal to the initial Consumer Price Index, CPI naught, times 1 plus the rate over 100 raised to the power of n. N does represent time, and it is time measured in years. So if we're told that the CPI was 150.3, so this is our initial CPI, so CPI naught, in the year 1995, and then it rose to 170.6 in 2002, that would be the current CPI in 2002. So we started at 150.3, we rose to 170.6. We can assume that the inflation rate remained constant, so we're solving for just a single R value. That's what we're going after here, R. You do have to read between the lines a little bit. The amount of time that passes from 95 to 2002 is 7 years, so our T value is 7. So knowing that CPI is 170.6 and CPI naught, or sub-zero, is 150.3, and our T value of 7, we've now filled in everything but one letter in this equation. Now, even though we're dealing with an exponential equation, the variable that we're going after is not a variable in the exponent. This is still acting as a value in the base of that exponent. It's not being raised to any power of r. So we're not actually going to use a logarithm to solve this. You may see log off to the other side, but that's for another part of this problem. In this case, I know that working through the opposite of the order of operations, I'm going to divide by 150 to move this number to the left-hand side. Then I'm going to take the cube root, or this, I'm sorry, not the cube root, but the 7th root to eliminate the power of 7. After that, I'll subtract 1 from both sides of the equation, and then ultimately multiply by 100 in order to isolate the value r. Now, in my opinion, I think you should show as much work as necessary. But one thing that I do want to see is that since I'm counting on most, if not all of you, to use a calculator to solve this question, at least show me what you intend to enter into your calculator. If you just give me the R value of 1.82 coming straight from this expression, I'm going to question how you arrived there. Now you'll notice that I did all of my work in one step. I did the mental explanation of all of that, but at least I showed this intermediate step implying what was typed into the calculator. That would be sufficient for the amount of work that I need to see. This shows me that you have an understanding of the algebra necessary to isolate R, and you recognize that in order to solve this exponential equation, we do not need a logarithm whatsoever. So after I enter this into the calculator, I get several decimals, but the end result is 1.2 8263. The instructions do ask for 2 decimal places as the result. So we're going to say that the rate of inflation for this time period was 1.83%. We'll round to the second decimal point. Now part B is just a little bit different. This time we're saying that the consumer price index will reach 277 in some year that's unknown. We would like to know how much time it takes for the consumer price index to rise to 277. So this time around, we're saying that the CPI value will end at 277. We know that it started at 150.3. And remember, this was in the year 1995. We'll keep that in mind. We just calculated the interest rate, and let's see here. They're not real explicit with this, at least not in the instructions down here, but this commentary right here does say using the inflation as from part A, go ahead and calculate B. So we're not going to use the extended result that we may have gotten on our calculator. We're using the actual result that we got from part A, which was 1.83%, and that's why we're using it in this expression here. Unlike the prior two expressions, R is reported as 1.83 rather than 0.0183, and that's because this particular function does account for the moving of our decimal point by utilizing this division of 100. So we have an R value of 1.83. This came from part A. And now our objective is to solve for n. How many years after 1995 does the consumer price index reach 277? Well, in this case, we need to isolate n, which is sitting as an exponent, so I know a logarithm is necessary. One of the first things that I'll do, however, is I'll divide 150 to the other side of the equation just to move this to the left-hand side. This will isolate the base value times some exponent. Now here again, I'm not interested in what this base value is. I'm not going to reach for a calculator. And I'm also not interested in finding what 277 divided by 150.3 is. I'm not going to take the chance of keying in a number incorrectly or reporting a number incorrectly off of the calculator. So I'm going to rewrite the remaining exponential expression as a logarithm, and the logarithm has the same base as the exponential, so 1 plus 1.83 divided by 100 is the base, and we're evaluating this at the result, the value that's over here on the left side of the equation. Now keep in mind that the value is not 277 anymore, but it's 277 divided by 150.3 because that number had to be moved first. This expression, when entered into the calculator, does give me several decimals after the fact. When rounded to 2 places, we get 33.71 years, or approximately 34 years. I wouldn't necessarily round this up to 34 years, because if we're in the year 1995 and we add 33.71 to that, we're in the year 2028.71. So we're in the year 2028, but we're getting closer to 2029. We're not quite at 2029 yet as a year, but we're in the year 2028. And so this answer here is not 33.71. That's not what we're after. We're not looking for the t value, but we want the actual year, and the instructions did say to round to the nearest whole number. And that's why we like 2028 as the solution. So here again, it's a pretty interesting equation, one that we're not completely confident in, I'm certain, because we're not studying economics in this class. However, the behavior of the function, the methods to solve for an unknown variable, that's the most important. For part 5, we have the same consumer price index formula. This time we're solving for some n value, the length of time needed in order for your CPI to double. Doesn't matter what CPI initial value we start with. When we divide both sides by that initial value, we're left with 2, and rewriting this exponential as a logarithm would allow us to solve for n. This question does ask for us to indicate the number of years that it takes to double. So when the calculator spits back an answer of 26.0172, I would likely return a result of just 26 years. Now for the last problem of the video, I'm just going to talk through question number 6 here, because some of the other questions act much the same way and others are virtually identical to problems we've seen before. But I chose this one to discuss in this video because part A and B are pretty interesting. We're going to use the calculator to establish some formula, some exponential growth formula for us in this format, y equals a times b to the x. And again, that would be the same as y equals c times a to the x power that I've been referencing in class. But as soon as we're done with that, we're then going to rewrite or express the function in the alternate form. And this again is just meant to serve as a reminder how these two forms, technically 3 forms now if you consider this one different, these 3 forms are all the same. They all produce the same end result, and we can use any one of those individually. And it's good to be familiar with all of the common forms. So let's remind ourselves again, in order to find an equation based on existing data, we need to reach for our calculator. I would probably create a new document at this point and not save the prior work. But we need to start with a list and spreadsheets page, so I'll choose option number 4. Right off the bat, I'm going to label my columns. And in this example, we have time and population as our 2 columns. And I'm going to copy the information. From the first column, I have these values, and from the second column, I have these values. Now, if you've practiced much with these exponential growth problems, you might be able to determine what the equation should be based on looking at the growth in the y column, or in this case, the population column. However, these values here really only indicate our growth rate if x is growing at a continuous value or continuous rate as well. So the fact that column A, number 1, changes to 2.5, or it increases by 2.5, and then we increase by 1, and then by 1.5, because the growth of each of those columns is not, or each of those rows is not consistent, then guesstimating what the growth rate is going to be a bit more challenging. So we rely on the calculator to do this. We've got the data entered. We'll press Control Doc to add a new page. This time we'll select Data and Statistics page. We'll specify that we want time along the x-axis. That was our first column. And we'll allow for population along the y-axis. And this data does appear to be roughly exponential, so we'll ask the calculator to find the line that fits this particular data. So if we go into Menu and then choose option 4, then option 6 for regression, we can specify the logarithmic or exponential growth that we're after. In this case, it looks exponential to me, not logarithmic. So we'll choose exponential, and this calculator is set to display at least 4 decimals, and I'm in pretty good shape because the instructions here do ask for 4 decimal places this time. So as we would report straight from our calculator, y is equal to 0.1513 times a, which is 1.3541 to the x power. I said a, but according to Math Excel, that's in position B. But they all do, again, like I said, mean the same thing. This c and this a as our base raised to the power of x. Here again is why I find this particular expression this particular problem so interesting. I'm a big fan of this particular format, f of x equals c times a to the x power. But in class last week, we talked about this format too, slightly different. I think we said a of t equals a naught but we'll use n naught, e to the kt power as given to us here. This c value and this n naught value are identical. The a value and e to the k power are identical, and t and x are identical. So if we wanted to rewrite this expression, if I wanted to convert it from the format that Mr. Ehrman generally uses, this guy right here, and then rewrite it in the format that MathXL seems to like, well, we can do that. We know that n naught and a are exactly the same. So I'm going to call this n of t equals 0.1513. But then I'm also going to note that a, the base, is equal to e to the k power. And we just said a moment ago that a was 1.3541. If 1.3541 is equal to e to the k power, and my job is to solve for k. K is the unknown. E is some value, some numerical value. Well, I can apply a logarithm to both sides of this equation and rewrite this exponential. We'll call this the natural log because that's the logarithm with the base of e. The natural log of 1.3541, and that should equal k. Now I would be a bit nervous here because when I enter the natural log of, let's see here, I'm going to have to create a calculator page, so bear with me. Control Doc calculator. When I do calculate the natural log of 1.3541, this decimal 3541 has already been rounded, so when I press Control Enter here, I'm losing some accuracy again, 0.3031. So I'm going to call this e to the 0.3031 times t. I would probably try this as the answer in MathXL first, just to see how it goes. If they'll accept it, great. If they don't accept it, then what we'll have to do is we'll have to backtrack and likely turn on a larger number of decimal points for our a value coming off of the calculator. Now if I go to the graphs page here, I see that I've got 4 decimals on display. Well, if I jump into the menu and select settings, notice I'm not going to the main menu of the calculator. I'm just going to the menu within this page. That way I'll only change the number of display digits here. Right now it's set to fix 4, but as I said in class, if we go at least 2 decimal places beyond what our final answer should be, then we'll probably be in good shape. And I could use 1.354111 as my number in the calculator. Whoops. Go to that calculator page. 1.35411. And now when I calculate it, I've got a slightly more precise result over here. As it turns out, when I round to 4 decimal places, I don't get a different result. 3031 is still the same. So we would have been lucky here if we had chosen this as an answer for part B. And if I pull up the answer key that I've got stashed over here, well, there we go. Here's our answer for part A, which looks pretty good, and our answer for part B as well. For the last part of this question, it does ask us to graph the data and then use the function to answer this particular question. So let's just keep in mind that when selecting the answer for part C, we already have a graph that's been created for us. So if we double check the scale, X scale and Y scale, as well as the location of the data points relative to the curve, we ought to be able to select the proper answer for part C, which may look like a bit of a toss-up between A and B because the data points look so similar, but this middle data point appears to be the giveaway. It wasn't that high above the graph. So I'm going to go with part A. And really, those data points do look awfully confusing. I guess really the giveaway here is where the graph touches or crosses the y-axis. We know that the exponential function should cross at 0, comma c, our initial value, and it almost never crosses at 0, 0 itself. So 0, 0. I think that might be the largest giveaway here, since A and B look so similar. So the final part of the question, or I guess two parts here, can be solved by using the graph of this equation. Now I probably won't graph it here in the data and statistics page. Instead, I'll probably create one more page. I'll create a graphs page, and I'll rewrite the function 0.1513. And now it doesn't matter which function we use because they're both going to be the same, either answer A or B. But I'll go ahead and use answer A since that's the first one we found. 1.3541 raised to the power of x. And I can use this graph to answer parts D and E, although I had a mistake here. Let me fix that. It's not times x, this is to the x power, so we better put a power of x. There we go. So after 7 hours, we can find out what the population is. And this would be easiest to do if I trace along this graph. So we'll go to Menu and choose Trace, which was option 5, and then select Graph Trace. If we're lucky, we can press the right arrow until we land precisely on 7. But to be honest, I think the easiest thing to do is just type the number 7. As you write that, a text box will appear on the screen. Tap Enter, and the calculator will center on an x value of 7. And we now have a population result of 1.2629. When rounded to 2 decimals, we'll just call this 1.26 hours. And finally, part E. If I go back to the graphing calculator and press the Tab key, this will bring up another formula bar for me. Our target is to find when the population will reach 1.35. 1.35. So I'm just going to create this second function equal to 1.35. That creates this horizontal line which represents our target line, and we want to know what x value is going to create an intersection at these 2 points. And with the menu option, number 6, to analyze the graph, we can find the intersection between 2 points. That appears to occur at time 7.2198, or 7.21, well, 219 rounds to 22 hours. Just realized something back here at part D. We're not talking about 1.6 hours. We're actually talking about the population in the Petri dish, and it's not real clear if we're talking about hundreds or thousands or millions of these bacteria, but we'll just leave the answer at 1.26. For part E, I am happy with 7.22 as the solution. 7.22 does represent time in hours. The remaining 2 questions I think can be accomplished in much the same way, so go ahead and try those on your own for the practice, and if you've got further questions, feel free to reach out to me and I'll do my best to help. Thanks for watching.